all, I'm Chandler. I'm the Director of Engineering at Logixboard. And today I'm going to walk through a story with you about how Logixboard's integration systems started out simple and sort of iteratively grew into a complicated beast with poor failure modes and limited observability. We're going to talk about how we rebuilt that system from the ground up on Temporal. And in particular, I'll walk through how we use Temporal's primitives around order guarantees and the patterns we built up around those primitives. The implications of these primitives are not so obvious in my opinion, but they're really powerful and they're an essential part of why our system behaves well today and operates effectively. So I thought it was worth sharing. There we go. Okay, first a little bit of context. So Logixboard is a white labeled customer experience product for logistics service providers. Basically, our product sits on top of ERPs, and we have all of these integrations into ERPs to pull in live data from our logistics service providers and offer a sort of real-time, up-to-date view of people's supply chains to our logistics service providers' customers. And these ERP integrations, they really sit at the core of the value of Logixboard. We started building them in 2019, and when we started building them, they really started out relatively simply, as you can imagine, like a webhook handler that saves some data. That's really it. But as the needs of the business grew, the integrations became more complex. They started to grow and became difficult to manage, and that's really what we're going to be going over today. So I wanted to talk a little bit first about the existing system and give you some examples of how it sort of slowly grew into that beast I was referring to. So when we built the first version of our first integration, we decided to use Kinesis and Lambda. So basically, anytime an ERP sends us a message, we put a message on a Kinesis stream. There's a Lambda function whose primary responsibility is parsing that message, mapping it to Logixboard's data model, saving it to Logixboard via an API. This started out relatively simple, like I said, and we went with this architecture for plenty of reasons, but the ones that are relevant to today are we wanted order guarantees, and these order guarantees kept our data processing logic pretty simple. We didn't have to account for out-of-order messages when we were saving data to Logixboard. And then the other thing worth mentioning is we could have just had the event listener write directly to Logixboard core API, but some amount of queuing was very important because these ERPs had really unreliable retry strategies and availability. And even worse, in some instances, customers had what they called middleware that they had built themselves in between the ERPs and Logixboard, with sometimes no retry strategies at all and really poor failure situations. So we wanted our ERP-facing systems to be really highly available. So that's why we went with queuing. But as our system grew, we encountered a bunch of situations that revealed undesirable properties of this originally simple architecture. And first, I want to talk with you a little bit about error handling. So when we built the system, we naively thought that errors that completely halted message processing were going to be infrequent. That was naive because it turns out 4 years into building these ERP integrations, even today, for the integration we started building in 2019, we still regularly encounter messages. Literally this week, we've encountered messages with surprising message formats, different data edge cases that we haven't encountered before and we didn't know when we're undocumented. So we try to program defensively, and it's not really lazy programming. It's really the reality of integrating with undocumented legacy APIs that error handling needs to be a first-class citizen. So to make error handling better, we added a DLQ to our system. So you can see the architecture diagrams getting a little bit more complicated here. Whenever the Lambda failed 3 times to consume a message from the primary stream, it put that message on a DLQ, continued processing the remainder of the messages in the stream, and the DLQ consumer tried to replay these messages at a more aggressive backoff when they were retrying. Had a really great property that data edge cases we were encountering in 1 or 2 shipments out of the many thousands that we're processing would not halt data processing for all shipments, but there were some downsides as well. Whoops. So one of them was that order guarantee property that I talked about. We lost that in this system. You have the DLQ consumer, which could be processing old messages for a given entity, while the sort of primary consumer is still processing messages as well. So our data processing logic became more complicated. And the other thing is outages, either of our dependent systems, like the core API or others not pictured here, or sort of simple logic failures would result in flooding the DL queue with messages. And it really made it harder for our system to recover from these types of situations. Okay, so that's error handling. And I want to talk about another situation. So imagine we have a message coming in from an ERP for shipment 123. And shipment 123 is related to organization or customer ABC. Now in our system, we need customer ABC to be present in Logixboard before we can save anything about shipment 123. And a sort of example of why we might need that is, imagine we're sending email notifications upon receiving a new shipment. Say, hey, your shipment has been created. Track it here, for example. But the recipients of those email notifications might be based on information related to the customers that the shipment is related to. So customer ABC is not present, so naturally we have to go to the ERP and fetch that information to sort of backfill it into the system. But that gets more complicated because these ERP APIs, they're not the most straightforward, and many of them don't even offer a fetch API where you can say, give me the latest state for an entity. And all you can really do is post a message to that ERP and say, whenever you're ready, send us asynchronously a message on your sort of webhook thing that has the latest snapshot of customer ABC. So that introduction of asynchronous fetching or asynchronous snapshot delivery really introduces even more complexity into our system. And on our legacy system, we would basically just, if customer ABC wasn't present, we would request a new async snapshot of customer ABC, but because we didn't want to halt processing of all the other messages in the stream, we would also request a new snapshot of shipment 123 as well. And this worked okay. We basically cross our fingers that customer ABC arrives first, such that it's saved in our system. The next message we receive about shipment 123 can then use that object. But then we realized, adding more complexity, that there were situations in which the ERP was never going to deliver customer ABC at all due to some problem or some problem in those middlewares that I told you about before. So we then needed to account for the situation where they're never going to be delivered, and we're not just infinitely looping over and over again asking for shipment 123 and customer ABC. This caused a lot of load on our system when we encountered this situation, and also we got some pretty cranky emails from customers whose ERPs we locked up with our many, many requests. So we introduced a sort of circuit breaker mechanism where we save some state in our system and limit the number of times for a given entity that you can go through this process where you request missing data and re-request a snapshot. And so you can see how just the small thing of we need customer ABC to be present before we save shipment 123 introduces a lot of complexity into our original architecture. Okay, the final thing I wanted to touch on here is another way in which the sort of complexity grew. So we have this Lambda consumer. When it starts out, it's making exactly one write to the Logixboard core API. That's pretty simple, and we went in with the best of intentions. You know, the Azure Durable Functions guy earlier was talking about how functions as a service, Lambdas should do exactly one thing. But as the demands, kind of similar to ones I talked about earlier, as the demands on this data processing logic grew, and the sort of potential for this logic to be spanning across many Lambda functions, many invocations of those Lambda functions, we often sort of took a shortcut in the face of time pressure or just sort of managing complexity of the code readability to add more and more calls from the Lambda consumer to the core API. So in normal situations, this is fine, except when, for example, if the fifth call here failed, and we're doing these calls in sequence or even in parallel, and if the Lambda consumer failed altogether and you had to retry the full Lambda invocation, you end up wasting a lot of compute on your core API, on the dependent services of the core API, so our database, retrying calls 1 through 4 unnecessarily. So this was painful and expensive. And beyond that, we also had ERPs that were sending us really massive message payloads in the hundreds of megabytes of XML. So when we parse those messages, we end up spending a lot of compute doing so. and memory as well. And so if you just introduce a very small bug in a very small write to the Logixboard core API, you end up spending a lot of money as well processing XMLs over and over again. And there was actually one situation in 2022 where we were shipping good old Jeff Bezos here tens of thousands of dollars a day, just reparsing XMLs that didn't need to be reparsed in the face of a sort of simple logic error. Okay, so that's enough about our legacy systems. This was 3 examples, but you can see here, there's 5 or 10 other examples, and you can see here how this architecture sort of led us incrementally down to a path where our system is growing in complexity and the failure modes are starting to get worse and worse. And you can see here how we ended up with a sort of Frankenstein. So I have no doubt that we could have done things better. We could have adhered more strictly to our principles that we set out to build this thing with. We could have documented them more effectively. And we were in the process of exploring redesigns for this system to get better behavior when we attended Replay last year. And sitting in Replay, it became clear that we were thinking about Temporal incorrectly as just a sort of workflow engine or a replacement for step functions, but rather durable function execution was a super powerful primitive. And when we took a step back and thought about all of our integration systems were really just performing a series of actions in response to messages coming to Logixboard. So as those series of actions get more and more complicated, maybe they start out at the beginning and Temporal might feel like overkill, but as they get more and more complicated, durable function execution becomes this really powerful primitive for taming that complexity. So what does our architecture look like now? Very similar, except that our event listener signals and starts temporal workflows. And this part isn't all that interesting. What's really interesting here is the challenges we had to overcome to get to this point, and what this relatively simple architecture diagram enables for us as a business. And I'll circle back on those 3 problems with our existing system that we talked about earlier. But in order to understand how our temporal-based system responds to those 3 challenges, we really have to understand how we handled order and the patterns that we built up around order guarantee. So let's go on a quick journey talking about order guarantees in Temporal. There are really 2 things in Temporal that have order guarantees. Those are signals and procedural logic. So let's talk about the nuances of some of these things. So on signals, if you start a workflow and then signal it many times, Temporal pretty clearly will guarantee the order of the signals delivered to your workflow is the same order as the signals reach Temporal server. So that gives you some order guarantee properties. But there's a non-obvious nuance here. If we take this example here, you might think that the workflow would process activity 1, activity 2, and then move on to the next message. But what Temporal actually does is it guarantees the order of the workflow task of executing that handler between the start of the function and the first blocking activity, activity 1. And in most cases, actually, if you have more than one message, more than one signal going to an existing workflow execution, you'll have out-of-order message handling here. And what you probably want is process activity 1, activity 2, next message. What you actually get is many signals being handled in parallel and many activities running out of order. So that property alone is not enough. The second property that I mentioned, procedural programming, is maybe a more obvious one, but it is an important property here because Temporal does guarantee, of course, that activity 1 executes before activity 2. So if we combine these things together, you see a pattern that you're probably pretty familiar with if you've attended a bunch of other talks at Replay, which is combining signals with a loop in the workflow definition. And I won't go into too much detail here, but the sort of interesting thing that's worth mentioning is your signal handler is now synchronous, not asynchronous. And that's a really important property to avoid the sort of downfall that I mentioned of the previous example. And then the other thing worth mentioning is your workflow ID becomes a sort of hash key for your temporal workflows, for your queuing system, except that there's something really interesting here where you have a separate queue and a separate polar per hash key. And that may not sound like a big deal, but I think this is a pretty unique property of Temporal's systems. And what does that get you? That lets you have really dynamic parallelism. You can spin your polars up to have thousands and thousands of polars in parallel. You can spin them absolutely down to 0 when you have no messages left in a given queue. You also get these fine-grained order guarantees where you guarantee order delivery within messages for a given entity, which is pretty common for how order guarantees work in streaming systems, except that you lose or you benefit from not having a large blast radius. If you have an error in processing one of the messages from one of your queues, you're not going to affect other messages in your shard because your shard has only one hash key in it. And then the other thing you get is really powerful for us at Logixboard because we often get questions from our customers, why is this shipment out of date? Or why does this shipment have incorrect information? And now we can go to exactly one place in Temporal Cloud UI. We can look at all the messages received from a given shipment, look at exactly what we did with those messages, and much more easily answer the question that the customers are asking. This isn't entirely different from something you can get from diligent structured logging, but Temporal has it sort of baked in from the start, and it's been a really powerful tool for us. But there are limitations to this approach. So I haven't really seen all of these limitations sort of listed out before, so I thought it would be valuable to go through them together. The one thing that I'm sure you're aware of is Temporal's event history cannot go above 50,000 events. So if your system receives a spike in messages for a given workflow execution, the example I showed you earlier has the risk of basically getting too many events on the same workflow execution before you can process them, and you will hit the 50,000 event history limit. Fortunately, Temporal has continue as new. This functionality lets us basically get a fresh event history after processing something like every 50 messages. So really the only difference here is there's now an if statement inside your looping portion that says, for example, if you need to continue after 50 messages, continue as new, pass in the remaining queue that you have into your initial queue. And you can see there on the first line of the function, we are initializing the queue. So that works pretty well, except you might think there is a race condition here of what happens if we try to continue as new when there are lingering signals that have yet to be delivered to the signal handler. Fortunately, Temporal has sort of accounted for this. And when you try to continue as new with pending delivered signals, the server will reject the command from the worker and say, no, 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 you've got pending signals. I'm going to reject your continue as new. First, go handle these signals, and then try again with that workflow task that leads up to the continue as new command. That's fine and dandy, except that this introduces yet another problem where if you end up in a situation where your single workflow execution is getting more and more events over and over and over again, in a sort of short time period, your workflow execution might spend its entire time in this sort of loop where it's trying to continue as new, then it fails, and it's trying to continue as new, then it fails. Okay, and then the final thing worth mentioning is the temporal event size limit, 2 megabytes, 4 megabytes, whatever the number, depending on how your temporal server is configured, there is an event size limit. And so when you continue as new, passing in that initial queue to initialize the next execution, you do have to be mindful of this. You can get around this with codecs, and I don't remember what Temporal calls them, but you can get around this by basically storing the queue somewhere, for example, in S3, like the Datadog talk earlier today, but it's something you have to consider as well. Okay, so those are the limits of that pattern. How do we navigate these limits? Our entity workflows, is what we call them, are relatively low traffic. When we looked at it, we received maybe 500 messages at a max for a shipment across its whole lifetime. So for this pattern works really well. We're never going to receive tens of thousands of messages for a single workflow. We can scale dynamically out. This is a really great pattern. But we did also have some other instances where we needed to guarantee order for all messages for a given tenant in our multi-tenant system. And in these cases, if we encountered a failure of one of our dependencies, or if there was a problem in logic, the queues would quickly balloon in size, and we would run into a lot of these limits we described earlier. Even in sort of normal behavior circumstances, if we had to sort of handle a flash flood of messages, a spike, then we would get in that signal continue as new, signal continue as new loop over and over again. So we creatively came up with another pattern built on similar principles that we call the high throughput ordered workflow helper. In this function, we were thinking about what was the sort of fundamental problem causing our temporal workflows to struggle. And it was really that the workflow was managing the state of the queue. You get some really powerful properties of that. But if you were to move the state of the queue off of the temporal workflow, let the workflow become purely a polar of the queue, then you get some really interesting properties. One is you get effectively infinite queue depth, depending on the tool you use. So that's really powerful. You can avoid that event history limit. You also get higher throughput. So your polar doesn't have to be spending time managing the queue. It does a very little amount of time fetching messages from your queue and spending most of the time doing its data processing logic. And then the key thing here is we really wanted to maintain durable execution of the polar. If you think about an alternative where you had a traditional Kinesis consumer, for example, kicking off a temporal workflow, you lose those order guarantee properties if you want that durable execution. And this pattern maintains it. So what does that look like? This helper function is shorter because it doesn't have to do the queue management. You see, basically, it fetches a message batch. In our case, from Dynamo is where we chose to store the queue, loop through that batch, process the message, and then delete it from Dynamo, and continue as new once you're done with the batch. An interesting thing to note here is we chose to leverage Temporal's retry and back off strategy with error handling, so that if the message batch from Dynamo returns no results, it actually throws an error from that activity, which is a sort of expected state. It's not actually an error. But then we don't have looping workflows going over and over again, exhausting actions, not doing any data processing. Okay. So there are some downsides. Like I mentioned, there's some upsides earlier, but there's some downsides to this thing. One is we have some custom metrics surrounding our ordered workflow helpers. For example, queue depth is a really valuable thing to report on and alarm on. And some of these custom metrics are a little bit harder to get in this high throughput scenario. And that's primarily because you don't have worker code running at as many points in the lifecycle of a message. You're only really running TypeScript in our case right before you start processing a message. So if you get stuck processing a message from a queue and your worker is failing on an activity, you might not be reporting queue depth at all. So you might not see that queue depth climbing, even though it is in fact climbing. The other thing may seem like a small one, but it's actually a pretty big one. You now lose those signals in your temporal event history and in the temporal UI. For us, that was a pretty big loss because it was really nice to be able to see we received these 3 signals. We started processing this one. We failed. You lose that visibility. You now have to sort of correlate that from the temporal event history with any metrics that you might be reporting from your clients that are publishing messages or from the queue store. And this third one is the really big one. You get less dynamic parallelism. So in that other example I told you, you could scale out and scale down to 0 really easily. In this example, if you're using the high throughput ordered workflow helper, you need some process to start your workflow polars. And you could do that very frequently, but this wouldn't be a pattern that we would want to use a workflow execution per shipment. We would have hundreds of thousands of shipment polars running at any given time. So we only use this for examples, like I mentioned earlier, where we have one queue or one execution per tenant. And the number of tenants in our system changes relatively infrequently. So we can just have a cron job, which basically every few minutes just checks and makes sure that all the executions that are intended to be running are actually running. Okay, so now we understand the ordered patterns that we were using. And now let's sort of circle back on some of those limitations that grew into, or the complexities that grew into our system that we were describing earlier. Now, when we encounter errors, that data edge cases, dependencies being out of date, or dependencies being down, no matter what the errors are, we don't have to deal with DLQs because now our system in an entity workflow, it only blocks processing for messages for that entity. That's super powerful. That's actually exactly what we want. We maintain the order guarantee of those messages, so we get to strip out all that logic and all that complexity from our systems. And as soon as an engineer intervenes or the system comes back online, then messages continue processing from just that entity, and all other entities remain unaffected. So that's a really powerful simplification for our new system. The other is dependent objects. So no longer do we have to keep sending both the customer object and the shipment object back to the ERP and doing this looping thing that is sort of happening across Lambda invocations. Now, because we have durable function execution, we can just start a function, a long-running function that waits for customer ABC to exist. So we let back pressure build up for shipment 1, 2, 3, no matter how many messages we receive within reason, within a few thousand. It doesn't happen. But we relieve that back pressure as soon as customer ABC is present, and we can process all the messages for shipment 1, 2, 3. This has saved our on-call engineers a ton of time debugging problems and has really reduced a lot of the complexity inherent in our code and our system. And then the third thing isn't really specific to the order properties I was talking about, but now, of course, when a dependency goes down, we don't retry all 4 writes leading up to that dependency. We only retry that activity. So we're saving lots of money. We're not sort of stuffing the pockets of AWS stockholders. Okay, so we've got 3 takeaways here. One is the complexity of event-driven systems really snuck up on us at Logixboard. When we started out on this journey, we thought this was great. We had the best of intentions. They're going to be simple Lambda functions. They do only one thing. And then the reality of the real world, building systems, just makes that really hard. And Temporal gives us this great primitive set of primitives that lets us sort of tame that complexity, not just in one fell swoop, like we've been refactoring in the last few months, but in addition, over time, as our system continues to get more complex, we've already made some pretty dramatic changes to data processing logic on top of our temporal systems, and we've seen that transition go really well. We can maintain all of the elegance and simplicity of our existing system. The second is Temporal's order guarantee primitives seem limited, and they were the thing that caused us the most pause when we were thinking about adopting Temporal, because they're sort of unintuitive in their implications, but they're actually quite powerful. And I think you can actually build things that are expressive and sort of unique in their capabilities compared to many other systems surrounding order guarantees. The final thing is we really changed the developer experience at Logixboard. We had an order of magnitude improvement in our developer velocity in these systems. And if you're excited to come work on these types of things and others in the future, we're continuing to invest. And I'd love to talk to you if you'd be interested in joining us. And that's me. Thank you.